representing three-dimensional shapes. So now how can we draw the shapes that we've learned in a way that explains two-dimensionally what they look like three-dimensionally without having a kit on standby? One of the problems with drawing molecules is that it always kind of looks planar. So the way that we do this is by convention, the central atom is put always in the plane of the paper, and we have different methods of how we can draw the bonds to say what's coming out of the paper, what's going into the paper, what is on the planar side. So a straight line puts the bonds to the atoms as plane. So we try to put as many other atoms as possible on the same plane with the central atom to indicate a straight line. For atoms in front of the plane, so if we look like this, right? So if this, for example, is my plane, so for atoms coming to the front of the plane, so pointing out at you, that is drawn with a wedge. For those atoms behind the plane, that is drawn with a dashed line. Now, this can be way better seen through this little chart right here, and this is also in your book. So linear, trigonal, planar, and bent. Notice that these do not have any wedges or dashed lines because these are all planar. We start to have dashed lines once we get to tetrahedral, so when we have multiple electron groups. The dashed line means you're going into the plane, the dagger solid wedge means you're coming out, and then you have your two planars. Trigonal, pyramidal, bipyramidal, seesaw, octahedral, and square planar. No, when we're drawing three-dimensional, we're not showing the electrons. Here with water, you can see oxygen with the two bonds of hydrogen being bent, giving me the shape, but do you see the electrons? No, the electrons are hanging around on the top of my oxygen in the correct orbitals, but we can't see them. So when we draw three-dimensional structures, we do not show the electrons. Best way, let's practice that by also looking at if we can have multiple central atoms. So in this structure here, this is just another version of a three-dimensional structure. We have more than one shape. So I can't look at this and give you one shape. I have multiple arrangements that's causing this molecule to bend in different directions. I have this carbon, this oxygen, and this oxygen all causing a different shape of my entire molecule. So when you have larger molecules, you have multiple central atoms with multiple different molecular shapes. This carbon has 1, 2, 3, 4 electron groups, so it's tetrahedral. This carbon has 1, 2, 3 electron groups, no lone pairs, trigonal, planar. This oxygen is bent. We have the lone pairs of the oxygens here. Then this oxygen is also bent. This should be bent, and that should be, it's supposed to be oxygen 2 is bent because we have 1, 2, 3, 4 electron groups, 2 bonds, and then 2 electrons. In this, we have 1, 2, 3 electron groups, so this can be trigonal, planar. Now, we don't really have one that tells you when you have 2 electrons and just 1 bond. This oxygen doesn't necessarily affect the shape, but just know that these 2 electrons are there. However, the main ones that are causing the shape are the carbon, this carbon, because this one's bending that way, this one's bending down, and then the oxygen's bending the bonds upwards. So state the molecular shape of each molecule. So first, let's figure out how many central atoms I have. I have this carbon and this oxygen. So 1, 2, 3, 4, no lone pairs. This is tetrahedral. This 1, 2 bonds and then 2 lone pairs. This is bent. So these bonds are actually bent. How about here? Now let's fill this in. I know I have my electrons here and here. And my nitrogen also has a lone pair. Now it's important to do that because the lone pairs affect the shape. Now I have a central atom here, the nitrogen. I have one with carbon, and this oxygen. So this nitrogen, 1, 2, 3, 4. 4 electron groups. 3 of them are bonds, 1's a lone pair. Trigonal, pyramidal. 1, 2, 3, 4. 4 electron groups, no lone pairs, tetrahedral. 1, 2, 3, no electron groups, trigonal planar. 1, 2, 3, 4 groups total, 2 of them are bonds, 2 are lone pairs, bent. So you go, you find out which atom will all affect the shape, and then you assign the shape of them individually to all central atoms. Now putting both of those concepts together, trying to figure out the shape and sketching the geometry. So let's draw the Lewis structure for sulfur tetrafluoride. Sulfur, fluorine, fluorine, whoops, fluorine and fluorine. So I have boom, 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 and boom. I bond. Now each fluorine is in period 2, so I can only have 8. So I satisfy my octet on my fluorine. Cool. How many total electrons do I have? 6 plus 7 times 4, so 28, 6. That's 30, 4. So I have 8 times 2, 8 times 4 is 32. I need 2 more electrons, so I have my 2 here on the sulfur. Because sulfur is in period 3, I can expand my octet. Now what shape is this? I have 5 electron groups, 4 bond groups, and 1 lone pair. This is a trigonal bipyramidal shape for the electron group. What kind of a shape is it for when you have a lone pair? That is seesaw with a bond angle of less than 120 and less than 90. Now the way that I'm going to show this three-dimensionally is with my daggers and my wedges. So since it's a seesaw, I have my fluorine with my sulfur with my fluorine. Then I have my dashed wedge to go out of my plane, into the plane. And then I have my dagger to come out. And that's how I would show my three-dimensional structure. So now bromine pentafluoride. Fluorine, 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 and then fluorine. Boom, 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 boom. Now I have 7 times 5, that's 32. Excuse me, that's 35 electrons, plus the other 7, that's 42. I have 8 times 5, that's 40, so I have my lone pair on the bromine. Bromine is past period 3, so it can also expand an octet. Fluorine cannot. I have 1, 2, 3, 4, 5, 6 electron groups. 1, 2, 3, 4, 5 bonding pairs. 1 lone pair. So my shape is square pyramidal. And my angle is 90 degrees. So the way that I would show this is I have my central atom, and then I have my fluorines going out of my plane, my other 2 fluorines coming out to me, and then my planar fluorine. Last one. Iodide has 7 electrons, fluorine has also 7, but there's 4 of them, and then the plus means minus 1. So I have 7 plus 28 minus 1, and that gives me a total of 34 electrons. So I have my iodide, fluorine, 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 and fluorine. I just realized each one of these has fluorine in it. Now, I have to put this in brackets with a plus. 8 times 4, 32, so I put my extra electron on iodide, again for the same reason, because iodide can expand an octet. 1, 2, 3, 4, 5 electron groups. 4 bonding pairs, 1 lone pair. I have seesaw with a bond angle of less than 20 and 90. So then I show this exactly the same way as I did the other one. You technically don't have to put it in brackets since it's a three-dimensional representation. Awesome. One more practice problem. Now putting the concept of three-dimensional shape and multiple central atoms together. Determine the geometry about each interior atom in each molecule and sketch the molecule. So right here, these parentheses for this one just tells you the order of how this is placed. I gave it to you for the first, and then I wanted you to attempt it for the other two. So here we're given carbon, which is going to be with 3 hydrogens, then nitrogen, then the other hydrogens. So carbon, 3 hydrogens, nitrogen, and 2 hydrogens. Now in total, how many electrons should I have? 4 plus 3 plus 5 plus 2. That's how many? 14. 2, 4, 6, 8, 10, 12. I still need 2 more. Give it to my nitrogens to satisfy my octet. Now, what is my shape of every single central atom? I have my carbon as my central atom and my nitrogen. This is 1, 2, 3, 4 electron groups, tetrahedral, no lone pairs. This is 1, 2, 3, 4, but there's a lone pair, trigonal, pyramidal. So because there's 2 different shapes going on, this isn't the best representation three-dimensionally of what the structure would look like. So using the dashed lines and the wedges, I want to represent that. So I would have my hydrogen planar with my carbon, my dashed line, my wedge, knowing I'm planar with my nitrogen, which then has the hydrogen on the dashed and the daggered line, my lone pair being somewhere up here. Now let's do this one together, and then the last one I'm going to try and have you do on your own as an engagement question. So the last one will count for points. You will take a moment to answer that question through emailing it to me. Now, or commenting on the YouTube video. I'll give you more details tomorrow. So CH3, CO2, CH3. So I didn't tell you specifically the arrangement because I wanted you to practice learning that. So CH3, CO, and then C. So I know that I'm going to have my carbon and carbon at first. So I'm just dealing with this part. It makes sense for my hydrogens to be on the outside and then to my other carbon. Now what about the oxygens? Now I can bond to an oxygen twice. Since both of the oxygens are next to the carbon, I can bond to it like this. Then I can bond this oxygen to the other carbon, which will then bond to the other hydrogens. The reason I did it like this was because the 2 oxygens are right next to this carbon, so both of them want to bond to this carbon. The only way that I could bond them together is to put one on the outside of the chain and one inside the chain. Then you fill your electrons and you're satisfied. Now what are all your shapes? This is tetrahedral. This is trigonal planar. Here we have bent, and then we have tetrahedral. So we would get something like this. Showing you the different angles. Now this is not the best variation, but showing you how it's not planar like this because some of the bonds are in different 120 or 109.5 degree angles, changing the shape. Now try this one on your own and submit your answer to me. But this is putting everything together. Again, drawing Lewis structures, right? Making sure that you're satisfying the octet. Figuring out what your electron geometry, your molecular geometry are. Then how many central atoms you have. From there, how do we draw a 3D structure?